In this video, we'll talk about the mean value theorem, which is really the main reason for having Rolle's theorem, and is going to give us a lot of things in terms of what we can say about functions later on. So what is this theorem? This theorem says the following. If I have a function f that's continuous on the closed interval from a to b, and it's differentiable on the open interval from a to b, we recognize these as the first two conditions we had from Rolle's theorem. However, for this, I don't need the last condition. Then, what I get from this is there is a point C between A and B, so that f prime at C is the same as f of B minus f of A over B minus A. Again, doesn't mean there is only one, but there is at least one. Now, one way you can interpret the mean value theorem is in terms of instantaneous change and average change, or slopes of tangent lines and secant lines. So here, f prime of c is the slope of the tangent line at some point along the graph of this function, and the ratio on the right, f of b minus f of a over b minus a, is the slope of the secant line between the points at a and b. So this theorem really says that there is some point inside where the slope of the tangent is the same as the slope of the secant. In terms of a picture, if I have my function like this, I have the secant line from a to b, something like that, and the mean value theorem guarantees that there are points, at least one, along the curve where the slope of the tangent matches that of the secant. So somewhere around, say, here-ish, the tangent line matches the secant, and there's also one more somewhere around here. Right? But I have tangent lines that are parallel to this secant line through the endpoint. To prove this, we're not going to go through, but the proof, if you want to think about it, is apply Rolle's theorem to the function h of x, which is f of x minus f of a minus f of b minus f of a over b minus a times x minus a. This will satisfy Rolle's theorem. You can apply it and you'll get the exact result from above. What's more important here is what this gets us. And the one main corollary it gets us is the following. If I have a differential function, which therefore is continuous, on the interval from a to b, and f prime is 0 everywhere, then the mean value theorem tells me f is a constant function. That is, f of x equals c for x in the interval from a to b. It is always the same number the entire time. This seems somewhat obvious, right? This is sort of an intuitive property that we have. If my derivative is always 0, I always have horizontal tangent lines. Therefore, my graph needs to be constant. It needs to be a horizontal line for my graph. Well, the mean value theorem lets us actually prove that directly. How do we do that? Well, let's take any 2 points, x and y, in the interval from a to b with x less than y. Our goal is going to be to show that f of x equals f of y. Therefore, my function has to always be constant because for any 2 points I pick, they're always the same. Well, what does the mean value theorem tell us? Well, the mean value theorem tells us that there is a point z, so that f prime at z equals f of y minus f of x over y minus x. But because f prime is always 0, I know this is 0 over here. And since y is not the same as x, since y is bigger than x, I can multiply through by y minus x, and then get that 0 equals f of y minus f of x, or f of y equals f of x. So no matter what points I pick, they always have the same value, therefore my function's constant. Which is a great point to have. If I know the derivative is 0, my function has to be constant. A second result in this line is the fact that if f prime of x equals g prime of x, if they have the exact same function values for all x, then f of x is the same thing as g of x up to a constant for some c. This basically comes from applying the result above to the difference between f and g. That'll become useful later on when we get to talking about integrals. So an example of applying the mean value theorem directly is a problem like this. Find a value c that satisfies the mean value theorem for f of x being the function x squared on 1 to 5. What am I looking for? I'm looking for a value of c so that f prime of c equals f of b minus f of a over b minus a. Now, from a function f here that I'm given f of x to be x squared. So I know that f prime is just 2x. So this on the left side here is 2c. On the right, I know my b is 5, my a is 1. So this should be f of 5 minus f of 1 over 5 minus 1, which is 25 minus 1 over 4. 24 over 4 is 6. So 2c equals 6 tells me that c must be equal to 3. So c equals 3 is a point where the slope of the tangent line to this graph is the same as the slope of the secant line. If I draw the secant line, the tangent line at 3 should have the same slope. It'll be close enough, off a little because of my inability to draw, but that gives you the idea of why this should work to find this for the mean value theorem. That's the statement, and that is sort of how the mean value theorem works and what it can tell us about functions at this point. There'll be a lot more it can tell us later on.